direct math. Direct math is a single method, but it is effective. And we find the address space. If we have an example, the address space is 64 bytes. Block size is 4 bytes. Cache size is 16 bytes. We have a write-through method. We can see this is one example to calculate the number of cache size and the block size and the bits in cache. So we can find 140 bits is the result. This is the example. Okay, the cache parameters we can find offset is 2 bits, index is 2 bits, and the tag is 2 bits. So we can find per index or per slot has 35 bits. 140 bits can increment. This is an example. Okay, this is an image or figure in the example. We can find the left section is the cache, the right section is the main memory. So we can find the color. You can find 1, 2, 3, 4. 1, 2, 3, 4. This is a group. Yeah, 1 group, 2 groups,
4 groups.
3 groups. Yeah, there are 4 groups. We can find the example. We use 1 column as a group. If we use the 4 data sections, we can move to cache. Yeah, but if the data are not used recently, we must replace these data, move to cache. So you can find the cache slots exactly match the index field. This is main memory. Main memory should in blocks, so offset bits not should. You can find 1, 2, 3 color numbers. You can find we can take index field. We can check if valid bit is true in that row of cache. If valid, then check if tag. If tag match. Tag is the flag. Tag is a symbol.
Flag bit.
Yeah, flag. So tag and flag is to show the effective. Okay, this is the address successes array. We can find the sequence of memory address. Okay, we can find this is another example. This is worst case for direct math. So we can find direct math we call DM. DM is direct math. So we can find a code DM that holds 4 one-word blocks. We consider the main accesses 0, 16, 0, 16. This is another, or this is an bad condition. You can find 0 and 16. He has far distance.
Yeah.
So you can find if we have 0, we are missing. If we have 16, we are missing. So miss. This is bad condition. But this condition isn't regular because we find before the class we call locality.
Okay.
So 0, 16, 0, 16. This is not locality. So this is the condition we are thinking, and this is worst case. Yeah. So
if those bits like that, it will go.
yeah. So
Because all is missing.
So this is called the worst.
Yeah.
Yeah. But condition has condition. So in the ebook and some materials, we have discussed this worst case. Okay, this is comparison so far. We can find fully associative and direct map are two examples. Fully associative, we can find block can go into any slot, must track all catch slots on request slot. So we don't like slow, we like fast.
Yeah.
So direct match is a better method. Block goes into one specific slot. This is simple, but this is effective. Only track one catch slot on request. So we can find the worst case. May only use one slot, but this is not regular. Okay, we can see that associative catch and catch performance. Set associative catch, we can find that we can choose compromise. Compromise is an condition. We can find the compromise in Chinese we call 妥协 or 折中. We can find some things has shortcoming, has good things, but we can't only have good things, not shortcoming. So we have choose compromise. So you can find some people have some shortcoming, have good things. So in China, 人无完人. Yeah. So we can find this is more flexible than DM, more structured than SA. Okay, we can divide into sets, each of which consists of n slots. Memory block maps to a set determined by index field and is placed in any of the n slots of that set. We can find, we call n as associativity. Associativity is a noun of associativity. So this is the name or the term. Replacement policy applies to every set. Replacement policy we are discussed in former class. So replacement policy is effective and is safe. Okay, this is here we assume a catch of fixed size. We have three terms: offset, index, and tag. So we can find the offset is same as before. Is address, is some address. Index can instead of pointing to a slot, now points to a set. Tag remaining identical fixed. Okay. This is an 8-block catch configured. We can find this is one-way set associative. This is two-way set associative. This is four-way set associative. So we can find associative 1, 2, 4, and 8. What is one? Every row we have one tag and one data. This is one-way set.
Yeah. There are two tags.
Yeah.
Two
tags and two data.
Yeah.
This has 4 data tags and 4 data.
Yeah.
This has 8 tags and 8 data. But this structure is very complex because this structure is regular and used recently. But one-way set is simple, and in some conditions we can use one-way associative. Okay, this is block placement schemes. We can place memory block part in a cache that holds 8 blocks. So fully associative, direct map, and the two-way set associative can use. This is SA catch example. What is SA? We can find 2 WinSet associated 6-bit addresses, 1 word box, 4 word catch, and write through. This is an example SA catch. This is SA catch of the image. The image can show SA catch. We can find this has same class and the same section. This has the same section. You can find the blue and green can replace by main memory. So we can find this section can replace this section. This green section can replace this section. So we can set numbers exactly match the index field. So we can find this is 0, this is 1. We can use 1 and 0 to divide the catch to 2 sections. And the main memory show in blocks, so blocks offset bits are not shown. We can find in this SA catch, each block maps into 1 set is main ideal. Or each block maps into 1 slot. So we can see colors. He has two slots and 2 sets.
Yeah. Green and blue.
This is the address table, so we don't care. This is worst case in set associated. So we can find SA is set associative. DM is direct map. Worst case for DM, worst case for SA. We can find the repeating pattern of at least n plus 1 that maps into same set. We can find 0, 8, 16, 0, 8, 16. If we have the worst case, we have miss and miss because the distance from 0 to 8 and 8 to 16
is long
too
distance.
far.
Yeah.
So this is the worst condition. Okay, in lecture 16, we have discussed set associativity determines flexibility of block placement. He has fully associative, direct map, and n-way. We can learn 3 methods in catch, and this is the 3 methods in catch. Okay, we have continue lecture 17. In lecture 17, we have discussed multi-level catch questions. So we can find in lecture 17, we have continued to discuss catch. Please pay attention, multi-level. Multi-level is in this section. Multi-level.
Yeah, there are 3 types of
3 levels. In regular CPU, in regular catch, in current structure, we have 3 levels catch, 3 levels of catch. We can find LE, L1, L2, and L3 can show 3 levels. So 3 level catch is an effective method for solution the speed of catch. Level 1, level 2, and level 3. The fastest is level 1. The slower is level 3. Level 2 is the immediate. Okay, we can find this is the review of last lecture. We can pass. Okay, this is an alternate perspective or the method, we can search the name from search engine. Hash table.
Yeah,
Yeah,
after
hash table is very useful, and we can find hash function is very important. In hash table, hash function is very important for hash table. If we have used hash table, we have designed hash function before we use hash table. So you can find in hash function, after hash function, the hash can direct one index.
yeah,
One index can become some values, and these values are in one array. This is you can see this is one array and one dimension array. So you can find this is buckets of data engine. So you can find value, value, and value. This is key. Yeah, it's the key words.
yeah,
Okay, this is, we can find direct, map, cache. We can find each bucket only has one engine. And n-way set associative, we have n engine in each bucket. We have one engine and we have n engine. We like one engine because one engine is simple and the control is simple. So you can find this is TIO breakdown is the hash function. Fully associative, only one index or bucket which holds all entries. So these tags can be tracked in parallel through different from external training linked list. So we call this structure as linked list.
linked list.
Yeah, linked list. The linked list is similar like array.
Yeah,
Yeah, but he has this. This is the formula. The formula can tell us which is the first, which is the second, which is the third.
the
After that,
hash table and list are using in Java program.
yeah.
Yeah,
So in Java, you can find before 20 years. Today is 20 and 20.
yeah,
In 2000, in 2000, I am a student. Yeah, in the area of my student, we have studied Java. We have used Java, but before 20 years, so Java, the capability of Java is slow
yeah,
and very not useful because the integrated developed environment is not useful. After some years, Eclipse has opened and building. We like Eclipse.
yeah.
But after some years, I had become a teacher and become a doctor. So we don't use any studied Eclipse deeply because we have used time to study other knowledge. So you can find if you are you become engineers, you are like Java and Python. This program, if you like to become doctor, become postgraduate, and you can find your study knowledge is different. So after the study, you must become an engineer, teacher, researcher. This is different. So you can find this is linked list.
sir.
how many total bits
About
are
everything.
attended in the following page. We can find this has 4 methods. We have 4 methods and 4 choices. Right back will become dirty bit. What is dirty? You can discuss dirty. You can find dirty is duplicate.
Yeah.
You don't think dirty is dirty. Dirty is duplicate. In database course, dirty is regular. In your laptop, in your cell phone, the duplicate data is regular and irregular. So we don't care dirty, but we care the remain size in our laptop, in our cell phone. If your remaining size is slow and is small and small, you will find the speed of cell phone or the speed of laptop is become slow and slow. If you find this condition, you will clean the rubbish. So you can find some software can clean the rubbish in the operating system. In China, we use some software to clean rubbish.
Yeah.
In China, we have used 腾讯电脑管家. Yeah. Some software.
We use CC cleaner like that.
Several software can clean the dirty. Yeah. You can find some duplicate data.
Duplicate files.
Some dirty. Yeah. This can be controlled. Okay. This is some condition. Okay. We can talk about this is the agenda in lecture 17. Okay, we can find this is one question. Measuring memory accesses. Measuring memory access. In a machine without cache, time it takes to access memory is easy to measure. If we have not cache, it is easy to measure, but if going to memory takes 1,000 cycles. Every access is 1,000 cycles. This is simple, but this is not useful because the cache is very useful and we have cache. We need cache. What happens when we introduce cache? You can find every access first checks the cache can represent average memory access time. So we can find we use cache, we check cache. This is some hit, and so we don't need to check memory at all. Some miss and have to go to memory. So if we have a miss, we must go to memory to find our data. So the cache is first, the memory is second. Okay, AMAT is in time, average memory access time. So in China we call 平均存储访问时间 average memory access time. Some time is long, sometimes is short. So average can show the condition. So AMAT is average time to access memory considering both hits and misses. So hit is good, miss is bad. Hit time and miss time is all times. So we can find AMAT equal hit time plus miss rate multiple miss penalty. Miss penalty is the bad things. So we hope the miss rate is low and low and low. But the miss rate is existing. Hit time to check if the data we are looking for is in the cache. So if the tag checked and if the data In the cache, we think this is hit time. Miss rate is percentage of accesses of a program that are not in the cache when we look for them. So miss penalty is cost incurred by going to memory. So miss penalty is our penalty in
Cost incurred by going to memory.
condition. Okay, AMAT derivation. We can consider a two-level hierarchy, which has a cache and the main memory. In lecture 17, we have discussed multi-level. So the three-level is recurrent structure. In the past, two-level, one-level is existed. So you can find this is an equal. You can find this is AMAT equal hit time and this rate multiple this element. Okay, AMAT goals have two. Goal 1. Examine how changing the different cache parameters affects our AMAT. So hit time, miss rate, and miss penalty is important three parameters. Goal 2. Examine how to optimize your code for better cache performance. So you can find cache blocking, access patterns is two parameters. Hit time, we can find the time taken to search the cache for the text or information you wanted. You can find the contributing factors. How many comparisons do you have to do? You can find the cache size. After cache size decreases, the hit time decreases. But the cache size decreases. We don't decrease the cache size to very low. We can choose compromise. So we can find if we have small cache size, the hit time have some conditions, some regular conditions. Generally, as associative activity increases, so does hit time. So you can find we can use increase in associative activity. We can decrease in number of steps. Every result change in blocks, we have to look in more places for the same data. This is some conditions, some knowledge by some scientists. Miss rate, the fraction of accesses your program makes which do not hit in the cache, the fraction of accesses which require you to go to memory. Contributing factor are three: access pattern, block size or cache size, and reducing misses. Okay, this is some 3C. 3C is compulsory, capacity, and conflict. Conflict is condition. So you can find the compulsory is many names. You can find the code start, program migration, and the first reference. Yeah. First access to block, impossible to avoid. First access is missing, is very regular.
Yeah.
So you can find the effect is small for long running programs. So we can find that we can turn off the computer. Turn off the computer. The computer needs some time to turn on. This is very normal. So some servers can run and run after time and time. So you can find that your laptop can sleeping. The sleeping is very normal model. If we don't like turn off the laptop, we can sleeping. And the sleeping is in low efficiency. So after sleeping, you use the laptop very effective. The capacity cache cannot contain all blocks accessed by the program, so full associativity won't hold all blocks. Conflict, you can see multiple memory locations mapped to the same cache location, so there is a lack of associativity. Okay, the three things is design solution. We can find the solution. Clustering, you can find the increase block size in there is the method. Capacity, the increase cache size, increase associativity. So the three increments can give us solutions. You can find that this is different. This is increased block size. This is increased cache size. This is
associativity.
Associativity. So this is not same. So you can find what type of miss is it. You can find one question. How you pull this data into your cache before? Two answers. If we have the answer yes, would this have missed in a SA cache with LRU, list recently used replacement? This is another question. Another question, the answer of this question has yes or no. You can find that if we have yes, this is stop, this is a capacity miss. If the answer is no, we can find this is a conflict miss. If we have this answer, this is a complex miss. So the conflict, capacity, and the complexity, this is the three answers. Okay, miss penalty. We can find miss penalty is cost.
Yeah.
In Chinese, we call 代价. Yeah, cost is like money. Yeah, cost. We can find usually in cycles or the US dollar. In 2020, the US dollar is high and too low. So the cost of money is the normal cost and the normal penalty. If you like to eat, you must pay some money. So you can find usually in cycles or frequent fractions of a second of this. You can find that this is going to memory, but sometimes it is the cost of going to another cache. You must return and you must repeat this question, this sentence. You can find this is going to memory, but sometimes it is the cost of going to another cache. If we have several cache, we don't know the wanted data is in which cache. So we must search and we must go to cache and memories. So this is cost of time, access time. So you can find contributing factors. How big is your memory hierarchy? So the structure, if we have complex memory hierarchy, we have to pay more cost to find the data. So more steps equal more penalty for things. So we have more steps. We have designed simple steps. If we have more steps, the cost is low, is big and big. We don't like the cost to become big. We like the cost to become small and small. So you can find MP. This is miss penalty. The smaller block size can become lower MP. So we can decrease the block size. Yeah, so we can find this is regular is level 1, level 2, level 3, and memory. 1, 2, 3. Yeah, 3 cache. So find the data is an interesting topic for CPU.
Yeah.
CPU want to search the data from every memory. This is every memory. This is processor speeds. We can find the 200 PS clock. We can find this anything about 15 clock cycles. Miss rate of 0 to 0.02 misses all instructions. And the peak time is 1 clock cycle. Which of the following improvements will decrease our AMAT? We can find the three choices. We can change some things. Okay, this is the answer. We can find 1 cycle at 0.02 is
misses.
Yeah, this is miss rate. Multiple MP
Miss penalty.
So this is AMAT. Yeah, this is 2
clock cycles.
cycles. 200 PS is 1 cycle. So 2 cycles equal
400 PS.
400 PS. PS is this. In Chinese we call 周期.
Okay.
Yeah. This is a time. This is a time period. Okay, we can find which improvement would be best. We use 190 PS clock. So 2 cycles become 380. MP become 40. You can find this 50 become 40. You can find this has 360. If we have MR of 0.015 misses, we change this to this. You can find the result is 350. So this is the good.
The lowest
result.
one.
Yeah. So you can find we decrease the MR, the miss rate
Yeah.
is the best.
400 to 350.
Yeah, this is the best answer and the best result. Okay, catch performance measured using AMAT. So you can find AMAT is very important time for catch. So we can use AMAT to discuss, to compare some catches. We had lower AMAT, we had power catch. So we can find time is very important. Parameters that measure peak time, miss rate, mix penalty, HT, MR, and P is 3 parameters. Yeah, this is the equation. The 3 C's of catch misses and their fixes. We can find the compulsory capacity conflict. Okay, this is AMAT. So please discuss, please remember AMAT. Okay, we can talk multi-level catch. Multi-level catch is very useful hierarchy. So we can find minimize AMAT. To make AMAT small, we want to have a small peak time, low miss rate, and small miss penalty. It is hard to do all these at once. So compromise is exactly. We can't reach these conditions. So compromise is exactly. We can find the direct math catch have small peak time. Full associative catch have a low miss rate. Small blocks help with lowering miss penalty. So, too many opportunities to store data. You can find this is different model. A model. You can find a different model has different conditions. Can we combine all these things into one structure to achieve our goal? The answer is wrong. So compromise is effective.
Yeah.
We don't reach all conditions. Okay, multiple cache level is the answer. We can find with advancing technology have more room on chip for bigger level 1 and for level 2 and level 3. So this is multiple cache levels. You can find a higher number of caches are lower level. So you can find level 1 is closer to CPU. Level 3 is closer to memory. Yeah. So you can find multi-level caching is a way to reduce miss penalty. Picking the right kinds of cache can help reduce other AMAT factors. So the answer, this is the answer. The result of answer is the result is
Multiple cache levels.
Cache levels. Okay, you can find multi-level cache diagram. We can see whatever the operation. We can find return, store heat. We can find level 1, level 2, and
Main memory.
this has two levels.
Two levels.
Yeah. The blue and the green, the arrows show request for data, return of data. So we can find this is the request, this is the operation, and this is the return to data. This is the design conditions. Level 1 focus on low heat time. Level 1 can minimize heat time to achieve shorter clock cycle. Level 1 miss penalty MP significantly reduced by prices of level 2, so can be smaller even with higher MR. For example, smaller and fewer rows. Level 2 and level 3 focus on low miss rate, so as much as possible avoiding return to main memory. We had a heavy penalty. If we had a heavy penalty, this is not good. This is bad.
Yeah.
For example, larger and with larger block size, we can find the same as rows. So this is the design. Multiple cache AMAT. You can find this is the standards or criteria.
Belgium standard.
Yeah, standards
Yeah.
and criteria.
Criteria.
Yeah, this is the equation and the calculating.
Yeah.
Yeah, this is the level 1. This is level 2, and you can find for 2 levels. We can use this.
Equation.
Yeah, level 1, and
Level
level
two.
2. So this is the final calculating. Okay, there is enough, and the question we continue in tomorrow. Okay, the weather is cold. Please pay attention and wear more clothing.